Now let us move on to the next one here, which is very important. Attenuators here. What is this attenuator here? I think you people are very much aware of this attenuator here. Attenuator is nothing but here. What is the use of attenuation? We say that the signal has been attenuated here. What is the meaning of signal has been attenuated? Nothing but here signal has lost certain energy here, right? So what does the attenuator does here is that attenuator absorbs the transmitted signal here. Some part of the signal will be absorbed here. That's how it is going to attenuate the signal here. Or you can say that some power is lost here. So attenuators are the passive devices here, usually used to control what here power levels in the microsystems here. Power levels in the microsystem. If at all we wanted to have the 100% power here, let us have the attenuation mode. Let's say if at all we wanted to have only 50% of the power that has been transmitted from source to destination, now obviously we will have to absorb more power by the attenuator while it is being transmitted through a transmission line here. So in this case also we are having two kinds of attenuators here. One is fixed attenuators, another one is variable attenuators here. So in the figure, in this particular PDF, in the figure, you are able to see something called as a coaxial cable here, right? So in the coaxial cable, there is the outer layer here, which has been marked with the dashed lines here, and there is something, the inner core is also there here, right? There is one rectangular with the tapered ends we are having here. There is nothing but here lossy material, okay, lossy material on the center conductor. It is there, right? So this is nothing but here a film is there here, which is being placed at the center of the conductor here. Why it is being placed at the center of the conductor is to absorb the some of the power here. Okay, to absorb some of the power. This is how we are able to achieve the attenuation here. Suppose if you wanted to attenuate the particular signal with 2 dB, okay, 2 dB or 3 dB or 5 dB or 10 dB here. So what you have to do here is we have to have that particular attenuator here, which is going to attend only 2 dB. So the thin film is there, no? Thin film, which is mentioned as a lossy dielectric material, which is placed at the center of the conductor, which is going to attenuate only the 2 dB, or it is going to absorb that much power itself only here, not more than that here. So it is fixed one here. It is not a variable. We cannot increase or decrease the power transmission here, or the power control here. Power control, we just fixed 2 dB loss, okay, or 5 dB loss or 10 dB loss here. So that is what is fixed coaxial attenuator, it is called as. Okay, now how exactly this is achieved here is usually there will be some resistive film is there here, which is being placed at the center of this coaxial cable, which is made up of a dielectric strip here. Okay, so which is placed at the center of the waveguide here, and whatever the incident wave is there here, no? Okay, because of the incident wave, okay, or the transmitted wave which is going to be transmitted through this particular coaxial cable is there, no? There is some current will be induced into this particular resistive film here, or you can say the dielectric material here. Due to this, what is going to happen here is that there is some power dissipation here, which is going to lead to the attenuation of the microwave signal here. Okay. That's how we are going to achieve the attenuation in the fixed coaxial attenuator here. Okay. Now, and as you can see there in the figure itself, you were able to see that this whatever the resistive film is there, it is both ends are tapered here. That is sharp points are there here. No? Sharp points are there. That like a triangle we are having at the both ends here. Why it has been done here? This has been tapered to both ends here, just because to reduce, or you can say to avoid the reflections here, to reduce the reflections or to avoid the reflections here. What we have done here is that whatever the resistive film we are having, it is being tapered at both the ends here, okay, to reduce or remove the reflections here. Now this is what is the fixed type of what you can say that attenuator here, coaxial cable attenuator. Now let us understand another one, variable type attenuator. It is there here. So this is variable type attenuator is nothing but here again we will be having some certain resistive film will be there here. Okay, with the help of some screw here, micrometer screw here. What we are going to do here is microwave or micrometer screw is there. That screw will be attached to this resistive film here. So this resistive film will be moved okay, moved with certain distance here. Okay, it moved with certain distance here. That is either moving from forward or backward here based on the movement of this particular resistive film here. We can vary the, what you can say, that attenuation here. Either attenuation can be increased or decreased here with the help of this micrometer screw here. Okay, just pushing out and pulling out here, we'll be able to control, what you can say, attenuation here. Either absorption will be more or absorption will be lesser. Based on the absorption here, we can say that attenuation has been increased or decreased. If at all we absorb the more microwave signal, then that means attenuation has been increased here. If at all there is less absorption is there, then we can say the attenuation has been decreased here. Okay, that's why we can call it as the variable type, okay, attenuator here. That was fixed here. Only 2 dB loss or 5 dB loss here. We can increase here. Okay, either 10 dB loss or 5 dB loss, whatever we wanted to have based on the applications here, we can increase or decrease the losses here. Okay, now another one is there. Another one type of attenuator is there, which is very important from the point of examination here. It has been asked twice or thrice in the examination here. That is precision type of variable attenuator here. This is diagram and everything is there. We just look into this one here. Precision type of variable attenuator here. So I'll just look into the diagram itself indirectly, and later we will discuss here. So this is what we are having the diagram here. See, so this is what is a precision type of variable attenuator here. See, you are able to see the first thing we are able to see here is that we will be having a circular section here. Okay, at the center where we will have circular section represented as a capital C here. Okay, and both the ends are been tapered here. Remember, tapered is tapering in terms of the rectangular here. Okay, remember taper. That's why it has been written as RC1 and RC2 here. Just observe the figure carefully here. At one end it has been written as RC1, means there is a rectangular shape is there at this end here, and again it is a circular C1. Then at the center it is completely circular here. At other end again we are having a circular, but it is tapered again with a rectangular here. Okay, so this is what is there, RC1, C and RC2. Another things are there. Another things I'll just explain here. R1, R2 and R3. R1, R2 are nothing but a resistive card here. Okay, R1 is placed at the one end where there is a rectangular to circular conversion is there. Okay, R2 is placed at the center of this particular precision type variable attenuator, which is completely circular in nature, and R3 is placed at a point where there is a conversion from circular to rectangular here. Okay, so this is how you can explain the figure here. There is another point which I wanted to mention. TE1 dominant mode is TE10 here. TE10 has been converted to TE11, and TE11 has been converted to TE0. Whenever a wave is there in the circular section, it is having a dominant mode as TE11 here. Whenever it is there in the at the mouth of the two terminals here, it will be having a TE10 mode here. Okay, so now let us understand the functionality here, how exactly this functionality is going to work out here. Okay, so now what center of this resistive card is there, no? This resistive card, what it does here is that it can be rotated 360 degree here. Remember, this resistive card R2 is there, no? This can be rotated with a 360 here with respect to the fixed sections of the circular to rectangular or rectangular to circular transition here, RC1 or RC2 here. Right now, whatever the incident wave is there, obviously it will be transmitted from one end. That is, let us consider it has been transmitted from RC1 here, one end. So what happens here is that obviously there is an incident signal on the R2 card. When there is an incident signal on the R2 card here, obviously there is an induced current will be there in the resistive card here. This induced current, again, what is going to happen? It is going to be dissipated here as the heat here. Okay, and hence the attenuation is going to happen for the transmitted signal here. Okay, now if at all this resistive card is there, no? This resistive card R2 is placed perpendicular to the whatever the electric field we are having in the circular section here. Right, this is a center is nothing but a circular section is there here. Okay, imagine it's just like a pipe here. a water pipe. Inside the water pipe, you are having some metal piece, a resistive card is there here. If at all you place this resistive card parallel to the field, parallel to the field or parallel to the electric field which is there in the circular section means what is going to happen here is that, okay, so it will be having a negligible effect here, negligible effect here, but absorbs the components which are parallel to it here. Remember, okay, which are perpendicular components are been not absorbed here, is been transmitted here. Parallel component will be absorbed if at all we place the resistive card perpendicular to the field or electric field in this circular section here. Okay, that's how it has been excited with the TE11 mode here. Okay, remember TE11 mode here. Now, if the resistive card, like for example, if the resistive card which is there in the center of this particular section here is kept at certain angle here. Okay, we are having certain angle description is being given in these three figures here. Let us understand that one. We got output as what it is, E sine square theta here. That how exactly this comes into picture we'll understand here. Now let us understand that R2 is a resistive card here which is kept at the center section here. That is kept now in the with an angle theta here. If there is an angle theta with respect to the electric field directions here, okay, then the component what we call as E cos theta, okay, there will be two components. If at all I keep the resistive card with an angle theta here corresponding to the electric field here, then what is going to happen here is I will be getting two components here, E theta, sorry, E cos theta and E sin theta here. E cos theta is parallel to the card here and E sin theta is perpendicular here. So what is going to happen here is whatever the parallel component is there, it will be absorbed again. So what is going to happen? E theta is transmitted without attenuation here. So E sin theta, sorry, E sin theta is transmitted without attenuation. E cos theta will be absorbed. So E sin theta appears as the electric component here, okay, at the output here. That is, output is nothing but RC2. RC2 is the output here, okay, in the direction Z here. So it will be appearing as E sin square theta as a rectangular output here. So whenever so in that case here, what is going to happen here? I'll just, we have the equations here, equation to be written. So what we'll be having, the attenuation of the incident wave is written as alpha divided by E divided by whatever the sin square theta is there here. Okay, whatever the E has been transmitted and whatever that has been received at the other end here. So 1 by sin theta square is there. 1 by sin theta could be represented with the help of this S parameters as a, okay, S21 here. Okay, okay. Reference plane at O to 2 when there is a input voltage at the reference plane 1. That's why it is S21 here. Okay. Now, whatever the precision rotatory attenuator is there, it depends on what here, the angle of rotation theta here. Okay, angle of rotation of the theta of the respective resistive card here with respect to the whatever the incident wave we are having here. So that means here we can also say that S equal to S12. We are having only just two port are there now. So that's why S21 is equal to S12 we can write here. Since there is no reflection here, remember, since there is no reflection here, or there is a reflection component which is very less here. Okay, we are not having any kind of a standing wave ratio here, or VSWR here. We don't have any kind of that one here. So that's why S11 or S22, those are nothing but a reflection coefficients here, right? So that's why it is equal to or approximately equal to 0 here. And how exactly the S matrix will be represented here for this particular variable type attenuator, that is precision type variable attenuator here. So this is how the S matrix is equal to 0 sin square theta, 0 here. So this is how we can represent the S matrix of a precision type variable attenuator here. In the examination also, then I ask you the question like this, that you have to represent the S matrix for the precision type variable attenuator. Means you have to draw this particular figure, explain these 6 to 7 points here, and mention these whatever the S parameters are there here, right? This is how we can answer for this particular question here. That is precision type variable attenuator here. Okay, I think it is quite should be very clear here. Now, let us move on to the next topic here. That is quite a very simple one here. That is phase shifter. It is there here. What is meant by phase shifter here? A phase shifter is nothing but here again. This is also two port passive device here. Okay. So what is going to happen here is that there is a change in the phase here. Just change in the phase. How exactly the change in the phase is going to happen? Let me explain it here. So what is phase shifter here? Phase shifter is nothing but here. It is a two port passive device, okay, which produces a variable change in the phase here of the wave that has been transmitted through it here, right? Just changing the phase of the particular signal that has been transmitted through here. That is what is phase shifter here. Now, how exactly you are going to achieve this phase shifter here? Just observe the particular figure here. So you are having the dielectric slab here, okay, using the dielectric slab here, okay, which will be positioned with the parallel of the electric field here, okay, electric field here. So this is how the dielectric slab is there here, okay. This is this is the cross sectional area here, and this is the top view here. You can see the top view. This is the cross sectional here, okay. So you are able to see there is a certain dielectric slab here, okay. So this is which is kept parallel to the at the position of the maximum electric field here. Now, how exactly you are able to achieve this change in the phase here? Change in the phase here. So whenever we say that there is a microwave signal is there, we will be having this wave velocity here, okay. The particular wave microwave signal will be having certain velocity here. Based on the change in the wave velocity here, okay, based on the change in the velocity of the particular wave here, a differential phase change can be produced here when it is been compared with the empty waveguide here. That is how we are able to have the phase shifting using the dielectric slab here, okay. And remember here, whenever we say that two ports are matched, means how exactly two ports are matched? By reducing the reflection of the particular wave here, right? So that's why what they have done here is they have also done some tapering here. You can see in the top view here, there is one side there is some tapering here, and another side also there is a tapering here, right? So there is so if at all we wanted to have the no reflection, means we need to taper both the ends of this dielectric slab here, okay. So beta will be the propagation constant here. As you can see, beta into length, beta into L they have given here, okay, beta into the whatever the electrical length we are having here. So the phase shift is achieved. How exactly phase shift is achieved here? By changing the electrical length here, okay. By changing the electrical length here, we are able to achieve the phase shift here, right? Okay, right. So two parameters you remember here. One is wave velocity and the electrical length of the dielectric cable. Both are responsible for changing the phase here, or you can say shifting the phase here. So that's why there are equation that is been written here. Just wrote it down here. P1 and P2 they are equation here. Beta 1 and beta 2 here. And if at all there is thus differential phase here, okay. Differential phase, you can delta phi is equal to beta 1 minus of beta 2 divided by whatever the electrical length we are having here, difference here, okay. Then how exactly this S matrix would be represented here again? Ideal phase shifter is again, when we say there is no reflection, means obviously S11 and S22 will be always 0 here, and S12 and S21 will be having certain phase shift here, right? Okay, that's how we can write here regarding the S matrix here. The questions would be like this here. Write the S matrix representation of the phase shifter here. At that time, what you have to do here is you have to write this. You have to draw this particular diagram. Mention beta length. It is beta into electrical length, and mention these 4 to 5 points here, and also write this particular equation here. Okay. This is how you are able to answer the question regarding the phase shifter here. I think you should be able to understand phase shifting is changing the phase of the particular microwave signal that has been transmitted through this particular phase shifter here with the help of what here? Two parameters here, that is the velocity of the particular wave and also the electrical length of the dielectric here. These two are responsible for changing the phase of a particular signal here.